be here. I'm a co-chair of the modeling sub-team at IRPIC, and my modeling co-chair, Richard, is here. And, the Permafrost co-leads will introduce themselves too. So essentially, we all know that Earth system models have been improving, but there are aspects of it that have not gone, that can use a lot of help. And based on that, the National Academy also identified that as a need. And we also have researchers in the community who can talk more about it. So the idea of this particular meeting is to bring everyone together, brainstorm, see what the next steps are, and see what we can do. That's from where I'm coming in as part of the modeling team. So over to you, Christina.
Yeah, thank you. My name is Christina Shado. I'm the co-lead of the Permafrost collaboration team, and I'm also coordinating the Permafrost Carbon Network, which has addressed the Permafrost carbon feedback issue in models for quite some time now, and many of you are actually involved actively in these activities. And so one goal here also is to not duplicate any efforts, but to make it better and stronger and see where there are needs. And so I'm looking forward to hearing individual presentations, and I'm definitely looking forward for discussion. And my co-leads are Ben Jones, who's also on the call, and Miriam Jones, who cannot be here today.
If I may, I did see my co-lead. I did mention Richard Cullither from NASA, but also Wilbert Wire from Los Alamos is a co-lead for modeling, and he's also on the call. So, thanks. Over to you, April. And I request all these speakers to just provide a brief introduction about yourselves and then present.
Sure. Thanks, Renu. Thank you so much for the opportunity to join you today and have this discussion. So I am April Melvin. I'm a senior program officer with the National Academy's Polar Research Board. I also work with our board on atmospheric sciences and climate. And many years ago now, I spent a lot of time doing fieldwork in Alaska in the boreal zone on linkages between wildfire, forest succession, and soil carbon, including a little bit of permafrost work. So I come to this topic with a little bit of understanding, but not much. I'm not a modeler, and I'm really looking forward to this discussion to learn from you all and get a sense of what the academies might be able to do in this space that would provide value to the community and as Christina mentioned, complement the work that you all are doing and not be redundant. Before I get into the details of the workshop, I wanted to just provide a little bit of information about the National Academies. I found often people that aren't in DC are a little bit less familiar with what we are or what we do and who we are. And so I just thought that might be kind of helpful context to explain how we would go about developing this workshop and kind of some of the unique aspects that we might be able to provide. So if you could go to the next slide, please. So just at a very high level, the National Academies is a non-government organization that was established during the Lincoln administration to provide guidance to the nation on anything related to science, engineering, and medicine. We're probably best known for our consensus reports, which typically provide very specific recommendations to the federal government, but we also plan workshops, have standing committees, have advisory boards, and bring together groups for a number of other types of activities. Our committees are often developed through nominations from the relevant expert communities, and then we take those nominations and vet them carefully and think about the task at hand and all of the different types of expertise that we need to have on that committee to answer whatever the task may be. And this is the same approach that we take to putting together a workshop on permafrost carbon. We'd look to get the right experts in the room to develop the agenda, and then I would kind of coordinate them and help them walk through the process of developing the activity. We look for balance in addition to the expertise on these committees, and we also look at conflicts of interest and bias to make sure that we will be providing sort of an objective forum for these discussions. Next slide, please. So a few of the sort of unique things that we can provide is that we offer a high profile independent platform that can often help to elevate topics kind of above the research communities that are doing the work, where we have resources and connections with many broader groups of stakeholders that may be interested in the topic that we can help to reach. Also, for agencies that may support the activity, it provides an opportunity for them to share and showcase the type of work that they're supporting. All of our consensus studies and workshops have a written product associated with them. So this also goes through a peer review. So it's a readily citable type document and can serve as a communication tool for program managers, but also those working in the community, of the research community or other stakeholder groups. And last, I just want to mention that, we're often working on highly interdisciplinary topics where you are bringing together many experts that don't necessarily work together on a regular basis. And so we can kind of help to connect audiences that may not be communicating with each other on a regular basis, which can lead to new approaches to thinking about a topic and helping to advance whatever the issue is. Next slide, please. So just a last one on the academies. I wanted to kind of focus in a little bit on the Polar Research Board itself. We were established about 60 years ago now, and we're actually relatively unique in the academies in that we have a focus on a region. Most of our boards focused on subject matter areas. And so we often collaborate with other boards to make sure that we're have all the right expertise within the academies as well as in the broader community that are coming to the table to discuss the issue. So our climate board, as you might expect, is one that we interact with very regularly and share a lot of staff, but we also work with a number of other boards as well. And we do consensus studies, we do workshops, sometimes we do more public outreach and engagement type activities. And most of it is kind of focused at that science policy interface and communicating the science in a meaningful way to the policy community. And I just put a few recent report covers up here, and you can visit our website and learn more about us if there is interest in that. Okay, so if we can go on to the next slide. So shifting over to our workshop idea here, this actually has arisen through conversations with our advisory board. So we very regularly ask our advisory board for their thoughts on topics that we should be actively pursuing, convening some type of activity about. And they have expressed great interest in us doing something in the space of how we might better integrate carbon emissions into Earth system models. And so what I'm really hoping that we can do today is to hear from you on what you see are kind of the next steps and gaps that need to be a priority for being addressed, and help us think through what we might be able to do that's going to provide additional value to the activities that you already have ongoing. If we can go to the next slide, please. So I know this is not news to any of you, and I left out some science slides I'd shown previously because I'm not going to try to explain the science that you know so much better than I, but just kind of at a high level here, I want to acknowledge, that we know that many Earth system models aren't incorporating permafrost carbon emissions or feedbacks at this time, and that those that do are focusing more on gradual thaw and not looking at all at abrupt thaw. And I'll come back to that in a moment, because that's an area that we've sort of focused in on and would really appreciate some feedback on. And because of these reasons and what we know about the extent of permafrost carbon and what it could mean for future climate if it's released, we view this as a really important topic to get attention, both so we can project and inform policy decisions, and also kind of the societal impacts of those climatic changes. And also from the policy standpoint, I think we're very interested in how this can inform the development of greenhouse gas inventories, and more on an international level, kind of thinking about the targets of the Paris Climate Agreement and where there might be opportunities to make improvements in getting those numbers maybe closer to what they could be. Next slide, please. So this didn't come through very well in the conversion from the PDF to PowerPoint, but so I put this up here with the abrupt thaw because this has been kind of a topic that's been brought to us as an important one, and new science is telling us that it could potentially be a huge source of carbon from permafrost. And so I think what we'd really like to learn from you is the science advanced enough at this stage for us to even kind of have part of the conversation be about how to incorporate abrupt thaw into Earth system models, or are there other questions that might help kind of get the science to where it needs to be to make that step that maybe should be a focus of part of the workshop. So I just put that out there as kind of a potential thing that we'd love your feedback on. Next slide, please. Okay, so a bit of the sort of nuts and bolts of what we envision this workshop to be. So the goal would be to identify steps forward and advance progress in incorporating current understanding of permafrost carbon emissions and feedbacks into these models, possibly with an abrupt thaw component. We envision this bringing together sort of all the types of experts that are working on this topic, from academia, national labs, the federal government, whoever the right experts might be. We'd also like this to provide an opportunity to foster dialogue with policymakers who may be working in this decision-making space and help to kind of calibrate their expectations for what the research community can provide, and for the research community to hear kind of what they would ideally like to have. We'd also use this as a forum to foster participation and discussion that support greater diversity, equity, and inclusion in this area of research and policy. And last, I think as we've said a few times now, we would really want this to complement the work that you all are doing already. And so I think having this conversation today is a really important step in getting your input in a way that will help us make sure that we're not being redundant with all the great work that you are doing now. And the product of this would be a workshop proceedings where we would summarize all the materials that were covered in the meeting, but wouldn't provide any formal conclusions or recommendations. Last slide, please. All right, so this is kind of a laundry list, to be honest, at this point, of potential questions that we think we could address at this workshop, ranging from how we might bridge scales to what empirical data is needed to the role of remote sensing. What do we need for computational advancements to make this work? How do we deal with uncertainties? And I put this out there because we really want the feedback as to what direction would be most useful and is kind of most feasible based on where the science is. And that's my last slide. So thank you. And I'm looking forward to hearing the presentations and the discussion that will follow.
Okay, so Renu, I see you unmuted. I'm just gonna click through the slides until I get to David's slides. And who else was it?
Ali Coben.
Okay, I think that might be Charlie's.
So thank you very much, April. That was a great intro of where we can go, and I'm hopeful that we can have that slide with all the questions that you listed up on towards the end as people discuss the different aspects. So
I guess I'll start.
Charlie.
Yeah. So, okay. I guess so. Hi, everybody. My name is Charlie Coven. I am a scientist at Lawrence Berkeley National Lab, and I guess in relation to this conversation, I guess I have two slightly different perspectives. One, as an Earth system model developer, I've been working on the representation of permafrost carbon feedback in Earth system models for 10 or so years now, since my postdoc in France, and more recently, in the past decade since I came to LBL. And so I've been working on that, but also most recently, I've been working as a lead author on the upcoming IPCC 6th assessment report, where one of the things we tried to do is to do a better, because as April says, very few Earth system models include the permafrost carbon feedback right now. What we try to do is include as a sort of secondary, in other words, a subsequent step in the remaining carbon budget process, the estimates of the magnitude of the permafrost carbon feedback, and to sort of use the literature as it exists to try and quantify that, and then take it into account for the carbon, for this issue of the remaining carbon budget to different global warming levels and how that relates to the Paris Agreement. And so I guess from both of those perspectives, I think that, they kind of inform a little bit about what I think the key uncertainties are, at a kind of macro or meta scale. And I guess I don't want to get a whole lot into the processes part, because I think probably a lot of the subsequent speakers are going to talk about the specific processes and how they need to be resolved. But clearly there are a lot of missing processes that need to be represented in Earth system models. The second thing is this is a much more systematic exploration of the uncertainty. When we were putting together the IPCC report, we basically combed through the published estimates that are out there in the literature, but it's very much, ensembles of opportunity, and or sort of, just these discrete studies that all are done in different ways and don't include things like, what is the uncertainty of parameter X on this, or what is the uncertainty on process Y, and how do those influence things? And so I really think that as a community, and I think, this is a more general statement about the land surface modeling and carbon cycle feedback problem in general, but I think specifically about the permafrost feedback, because the numbers of published studies are relatively small. We need to do a much better job of understanding that uncertainty. What are the processes that control it? What are the parameters that control it? And using the tools that we do have. And lastly, in terms of things we were asked about, sort of what is the way forward? I guess a key thing that I would hope that we are building the tools currently and can leverage is this idea of sort of dynamic heterogeneity tiling, right? Land surface models have always had this kind of static heterogeneity tiling of different functional types or other ways of breaking up the land surface. But now we're developing through things like the FATES model that we're developing in the E3SM and the CESM, as well as other system models are doing similar things. This dynamic heterogeneity or disturbance heterogeneity tiling, whereby for example with fire, the model carves off a part of the landscape that burns every year and then tracks the subsequent dynamics of that separately. And so you get this constant, merging and splitting of the land surface in response to dynamic disturbance. And I think, fire is sort of the obvious place to start. Where, it's a thing that we're working on throughout the world, understanding the effects of fire and disturbance and subsequent succession that happens. In the permafrost context, linking that to things like soil carbon and soil physics that respond to that soil carbon, the thaw that occurs after fires, building in this kind of dynamic heterogeneity tiling that takes into account these kinds of processes, I think is a very promising way forward. And then I think, a key question is, can we do something like that for thermokarst as well? Meryturetsky's recent paper was basically, very similar to this kind of dynamic heterogeneity tiling of approaching thermokarst from this, if we understand that there are these landscape transitions that occur, but in a very, super simple way. Can we do it in a slightly more mechanistic way at a scale that's tractable for Earth system models? So I'll stop there. Thanks.
Thanks, Dave Lawrence.
Great.
And we're just going to keep all the questions for the end, questions and discussions at the end of the presentation. So.
Great. So yeah, my name is Dave Lawrence. I'm at the National Center for Atmospheric Research, and I've been actually working with Charlie for the last decade on the permafrost carbon feedback problem. And so I kind of have a similar view to Charlie, not surprisingly, about some of the things we need to do. And I guess I'm not going to pretend that I know all the processes that we need to add, but I'm just going to talk about how we're addressing it within CLM, which is the model we use in CSM, community air system model. And so I think my overall goal, our group's overall goal, is to include more realistic representation of the hydrologic and associated soil, biogeochemical and vegetation responses to permafrost thaw, ice melt, climate change, and disturbance. And in particular, so the way we're approaching it is trying to treat, subgrid representation, tiling, like Charlie mentioned, both from the perspective of the hydrologic processes. I'll introduce the concept of representative hill slopes, snow, and then vegetation processes that Charlie mentioned, as well, like fire disturbance. In addition, to deal with uncertainty, systematic assessment of uncertainty, perturbed parameter experiment that we're working on right now, I think is going to help us understand uncertainty. And then a few other things that are going on that I won't talk about. introducing moss and lichens, no redistribution of excess ice that Hannah Lee might comment on. Next slide. And actually move on several slides. I'm going to go to, keep going. I'm going to skip this. And next one. One more. Okay, so for the concept of representative hill slopes, and we're trying to introduce into CLM and the ability to capture some of the subgrid processes going on here. I'm showing a lowland on the left, upland on the right, and this is for a figure for proposal that unfortunately wasn't funded. But by separating a grid cell into these representative hill slopes, we can capture some of the key lateral processes that are going on in terms of snow redistribution and lateral water flow as the permafrost system evolves. And so on the top is indicating, how snow is going to be deeper in the depressions and how it impacts processes there. And then if you look on the lower left, you see a summer lowland system where you might have a water table not exactly at the surface, but then after ice melt and the permafrost thaw, that water table may come at the surface. We think we have the capability now to represent that in a dynamic way. And on the right, there's a system where in the upland where it may not be quite the same. There might be water being ejected from the system rather than sticking around. And so, trying to treat those two different systems independently. And, I think with this system, we can start getting at maybe providing some feedback onto like a thermokarst type thing without explicitly modeling all thermokarst. And then the next slide, just to finish off here. I think the other real key thing is a vegetation carbon gain from that we're getting, and the PCN MIP showed this really wide range of responses across different models in terms of the vegetation carbon gain due to the CO2 fertilization feedback. We know that a few of those models are probably wrong. We know that nitrogen processes are kind of complicating the whole picture. One thing, the way we're going to approach it is by running this very large perturbed parameter experiment to try to get an assessment, a good assessment in these really fully coupled biogeochemical models about what is controlling the CO2 fertilization rates in the Arctic zone. So I'll stop there.
Thanks. Now we can go to Bill Riley's.
Sure, thanks, Renu. So my name is Bill Riley. I'm at the Lawrence Berkeley Lab also. And I'm going to describe a little bit about ecosystem modeling, which is a more fine scale, potentially fine scale, doesn't have to be, but it's often used at fine scale, and mechanistic model. We go to the next slide, please. So here's just a quick overview of the model. One of the benefits with respect to this question of ecosystems is that it can be run in 3 dimensions, fully coupled. And I'll show you some examples where we run 2D transects, which are more efficient for some of these problems. It also has a very mechanistic treatment of many of the processes that we've been discussing, the soil biogeochemistry and the plant responses, which can be helpful in trying to interpret the effect of permafrost thaw on the longer term dynamics. Next slide. So an example of what I'm talking about here with respect to the hill slope type of simulations is shown. This is from a paper Zalal and McConan just published in JGR, where we were looking at a hill slope explicitly represented with interconnectivity of water and energy and nutrients, for example, and then using the model structure to inform why shrub expansion is occurring in certain parts of the landscape and not others. So the next step here, so this is all without dynamic topography. The next step, if you go to the next slide, is our development in the model allowing the topography of those different elements along a hill slope, for example, or in a plain to vary. And so we're doing that with the basic concept that when water moves into the subsurface in these systems and freezes, it can expand and either cause ice wedges, for example, in polygonal tundra, like you see up in northern Alaska, in Barrow or Utqiagvik now, or pulses as another example where you have more ice lens type formation, which can also, when it freezes, expand the soil upwards. And so we've developed this in Ecosys now, and if you go to the next slide, I'll show you some examples, quick examples. So this is one example at our site in Stordal-on-Meyer. This was originally a DOE-funded project and is now an NSF-funded project called the Emerge. And we're just starting this. This is really nascent work. And this example, which is blurry, sorry about that, in the lower right is for the pulsa part of this mire. So we have these relatively large pulses showing the deformation in the land surface, which of course is the first part we would need to do in these models to get at a more abrupt thermocause. thermokarsting. And you can see we're getting sort of reasonable 2 to 3 centimeter seasonal cycles of the ground deformation. And then if you go to the next slide, the other thing we really want to do is look at hill slope process. So that's a very flat system. This is an example also just starting of using this model at Daring Lake in Canada. So here we have a system, it's a real hill slope from a crest down to a lake. And I try to indicate here the relative differences in how we broke the landscape up in this interconnected grid with a fen down towards the lake. And what happens in the model now, and it may actually be realistic, over time is a water movement down the hill, accumulating in the fen and freezing, and then the soil moving up because of that freezing over the long periods of time. And you can see sort of the interannual variability and the seasonal variability in that ground deformation there too. So that's where we are with the model development. We're in the process. I was hoping to have some simulations to show you about abrupt thaw, which we're just developing now. If you go to the next slide, I'll just give you a sense of where we, the other question that was asked of us is, what do we need in order to test these models? One of the important things that in the individual site we look at, we need to know something about the ground ice, because we need to initialize the models in that way. And that's really important for the subsequent dynamics. So the other thing we need once we have that is data to benchmark the model. And so there are, and that the first order thing we need there are deformation time series, spatially explicit if possible. And I've been learning there are some methods to do this, and we're trying to assemble these for individual sites so that we can test whether the model is getting the right seasonal and more rapid, perhaps, dynamics in its predicted deformation. So I'll stop there.
Just excuse me while I go back on some of these slides.
Thanks, Bill. We'll have Scott next, and then Hannah Lee.
Okay, thank you. I'm Scott Painter, Oak Ridge National Lab, and I will, use my 3 minutes to describe some of our experience with the Amanzi ATS code and kind of touch on the questions that were provided. Focusing really on thermal hydrology as a kind of a precursor to understanding the carbon release questions. So ATS, or Amanzi ATS, is an open source and highly parallel code under development in the DOE for about a decade or so. It's a 3D subsurface coupled to a 2D surface, so integrated surface subsurface code. Does flow and energy transport, and then uses external code pFlowTran for biogeochemistry. One of the kind of unique aspects of this is it has a very advanced mesh infrastructure, which we put there specifically for Arctic applications, where we wanted to begin addressing some of the thermal karsting and deformation questions associated with abrupt thaw. So we have 2 modes for ATS. One is a fine scale mode where we can resolve, with some computational effort, microtopography and its effects on water and energy transport and solute transport. And then we have an intermediate scale mode where we average over some of that fine scale microtopography and incorporate its effects as subgrid representation of water flow on the surface. So with regard to the question about abrupt thaw, I think other presenters have already identified thermokarst, or mechanical deformation of the surface, as being the key challenge there. Because we have adaptive or dynamic meshing, we have tried to look at this and with only partial success. So it turns out to be quite a challenging computational problem at the fine scale if it's done mechanistically. So we're able to use our adaptive mesh capability to track changing topography as excess ice melts. And that works fine. We're able to then, conserve energy and mass as we move the mesh. However, we have always kind of had challenges that associated with mesh, poor quality meshes. So at some point, the mesh deforms to the point where it's difficult to move forward computationally at the fine scale. So that is quite challenging. Additional work definitely needed there for fine scale modeling. We took another approach after having only limited success there and moved up in scale, developed this intermediate scale model that averages over a lot of the microtopography and captures its effect and subgrid representations. And those subgrid representations are dynamic. So as low center polygons transition to high center polygons, for example, we can capture the effect in the subgrid. Regarding the question about representation of processes at different scales, I will just focus on one that I think is particularly challenging, and that's lateral flow. Obviously, as you move up in scale, you don't represent that directly, but its effect is still important. And so, there are various strategies for capturing that in subgrid models. It's probably more important in continuous permafrost regions where we know there's a lot of lateral flow because the frozen ground blocking infiltration. I think particularly challenging there is going to be capturing the transition from continuous to discontinuous permafrost in these upscaled representations of lateral flow. So that's something that we're thinking about on the NG Arctic project. And finally, we had a question about critical observations for improving our models or building confidence in our models. And I wanted to focus a bit on critical observations for evaluation of models. And I think some experience we had last year with ATS is instructive here. We did take a very detailed look at several types of observations from the NG Arctic project in Barrow, and we're able to get good matches with soil temperature at depth over multiple years, and also water level, measured water level through the summer over multiple years. However, when we looked at those results closely and started looking at sensitivity, we realized that we had some ambiguity in the parameters, that we could scan two parameters simultaneously and not affect the result. So specifically, we could change hydraulic conductivity and a parameter appearing in our bare ground evaporation model. And if we changed them in the right way together, they did not affect the result. This is a classic null space, which means their observations were really not able to constrain the model parameters. So then we went back and found there have been some measurements of evapotranspiration from the area. And then when we brought that in, we were able to match that reasonably well also. And then that was able to constrain our model parameters that had been unconstrained before. So I wanted to sort of describe that to you because I think it raises an important point of how critically important it is to have co-located observations over multiple years. And in particular, for this example, what we really need is runoff and inundation dynamics co-located with measurements of ET. So I think I will stop there.
Thanks, Scott. Last but not least, Hannah Lee, looking forward to hearing.
Yeah, hi, my name is Hannah Lee. I'm an associate professor at the Norwegian University of Science and Technology. I've been working for the many years in the past with Dave Lawrence to represent excess ground ice in model CLM. So we can simulate first order land surface subsidence from permafrost thawing. Here I'm showing you recent work from my group where we incorporated excess ground ice as part of tiling to represent subgrid scale processes, permafrost thaw processes, as what Dave and Charlie mentioned. So here we incorporated different amounts of ground ice into different areas within sections within a grid cell within the CLM. And then this represents different types of land formation, like ice lenses or ice wedges, and so on. They affect, so we were using this very old information about ground ice data. And then what it does is then we are showing, if you can see this bottom right figure, then we are showing different, with climate warming, we're showing different representation of where permafrost is thawing and how much has developed into talc and how much has fully degraded. But you can see that subgrid representation actually makes it a bit more variable thaw projections. Obviously, this work is not linked with surface hydrology, like what Dave was mentioning, hill slope hydrology. So that would be kind of the next step into our development. That's all from me.
Thank you all. I think that was the last presentation. Is that correct, Meredith?
Yes, it is. And I'll just move back to the questions.
Awesome. And yeah, thank you all for keeping the time so exactly. That's very nice. So we have 20 minutes left for discussion, and I can moderate this, but I also think you should feel free to type in questions into the chat box and raise your hand if you have a comment or something you would like to say. And maybe first, are there any specific questions to any of the speakers? No questions, that's fine too. Or maybe April and Lori, do you have an idea how you want this structured?
I mean, I think, well, thank you for those presentations. That was very helpful to start to get a sense of kind of what some of the most active work is in this space. And I think demonstrates to me that you are all thinking about all these questions that we have listed here. So I think, I guess, you know, from our perspective, you know, are there certain pieces of this that you think would be valuable for us to be addressing in a workshop? Are there groups of scientists that you're maybe not working with right now, but you think should be kind of pulled into this space that we might be able to help do that? Or are there any questions on this list that you think are absolutely should be prioritized, and having another group help to push it along and elevate it would be helpful?
Yeah, and I'll just add to April's comments. I'm our colleague at the National Academies. You know, we're not trying to actually answer these questions here in this forum. You know, the idea is to try to tease out, you know, a really fast forum like this is great for just sharing information, as you all have just done. But if you had, you know, a full day or a full 2 days to really sit down with particular groups and hash out, you know, and really spend time debating and trying to drill down and figure out what are the optimal steps forward to answer some of these questions, you know, who would you want to sit down with? What kind of groups need to be brought together that aren't naturally talking and meeting? And, you know, what are the kind of questions you'd like time to really work through?
I'll throw out one idea. Oh, sorry.
Bill, and then maybe Vladimir, who's raised his hand. Bill, go ahead.
Okay, I was just going to suggest it might be helpful for us to get a synthesis of observations together across different types of landscapes, maybe bringing in the observations that have been, like Vladimir, that have been doing this for a long time, because, you know, the models, especially their system models, are not going to represent each single site appropriately, but they should get the right functional responses to changing temperature and precip, et cetera. So having a synthesis of those types of observations handy for us would be really helpful.
That's more a request for field people, right?
Yeah, or maybe even remote sensing people that look at larger scales for, now we can see some of these deformation processes happening, or, people that have done repeat photography. And we have pieces of these type of things. But it'd be nice to have a synthesis appropriate for the scale of these larger models.
Vladimir.
Thank you. I think I have two comments. The first one, yes, abrupt change is very important, though it's still very limited in space, very limited. But it's hotspots, so it's important to include. No questions. What I really kind of not appreciate that the long-term thawing of permafrost is now treated as something not really important, and that's completely wrong. So thawing permafrost, when it starts to thaw, it's about 10-15 centimeters per year. So in a few decades, you can have permafrost thawed or talc developed, similar to what we have under thaw lakes, for example. So that's first thing. So don't forget about normal degradation of permafrost. And from here is my second comment is it seems like we feel like we already solved this problem. The permafrost distribution, permafrost thawing, kind of long-term normally without hot spots. And it's not true, really. An example is Hannah Lee showed this on her slides, distribution of permafrost change by the end of the century. But if you look carefully, there is no permafrost now in southern Alaska in this map. So it means that the climate models which include permafrost representation do not describe permafrost even distribution properly. So this is kind of step back for sure, and it's much less exciting than include abrupt thaw into these models. But I think we still have a problem with representation of permafrost in kind of coarse scale permafrost models. I'm sorry, climate models including permafrost. I think that should be still in a discussion. So it needs to be improved.
Yeah,
otherwise,
thank you.
Yeah.
I actually appreciate that comment. And this one thing does not mean the other thing is not important anymore. But I agree, it's a good idea to keep things on the radar still. Scott Painter and then Dave Lawrence.
Hey, thanks. I was really struck by the fact that all 5 presentations dealt a lot on thermal karst and sort of mechanical deformation processes in general. And to me, that's one of the really big modeling challenges we have left, and an obvious topic for a workshop. And related to that, but maybe slightly different, I think one of the really huge challenges is how to model the transition from continuous permafrost to discontinuous permafrost. I think that's really hard, and it's probably going to be quite important to capture.
Mm-hmm. Great, and I in the request for presentations, thermal karst was in the email, so that's why also everyone was nice enough to address it. Dave.
Yeah, I want to follow up on what Vladimir said, and just to make it clear, yeah, I don't think we're getting to the point where we're ignoring those fundamental, the large scale permafrost degradation that we are anticipating. And, we don't have time to present it, but I'm viewing this subgrid effort that we're working on, across different things in terms of the vegetation and in the soil properties as a means to that, and especially like the discontinuous permafrost. So what the hill slope model will provide is the ability to represent in these models relatively cheaply compared to going to ultra high resolution, the impacts of aspect, slope, lateral redistribution of water on the thermal properties of the soil. And so I do anticipate that when we've implemented this fully, that we should be able to start seeing that transition between continuous and discontinuous a little bit more realistically, with all the problems that you would still have with the large scale forcing that you get an Earth system model. But we are already seeing a richer array of soil temperatures and so hydrologic conditions. So I think that's promising. And the other thing I think that we didn't get a chance to discuss here is just snow. And we just have to keep coming back to that, because the representation of snow is going to have such a strong influence on permafrost. And we've seen within CLM that going from one, CLM 4 to CLM 5, where we change some snow density parameterizations, a really big impact. And that's without even taking into account for like snow redistribution, which we also know is quite important. So I would say some work on snow would be important.
My question to this conversation would be also, is there a project, an activity that wouldn't happen if there was no National Academies workshop? Or can we push something forward because of a workshop? And I'm not sure how we can identify that, but that's something to think about.
And that's a question for all the panelists who prepared, presented, and for others. Yeah.
Ethan, you have your hand up, and then Charlie Coben.
Yeah, so I think it's worth emphasizing the other aspect of Bill's comment about the sort of synthesized observations. A lot of the fine scale work and the fine scale modeling that was shown, and especially when partnered with a lot of the fine scale work that's being done in Europe, is still focused around specific sites. The Lena is well studied, the Barrow obviously is well studied, right? There's different areas which are well studied, but having synthesized products that would allow models and observations to kind of come together on common modeling efforts at that finer scale, I think would add a lot to this community. We know we're doing well in Barrow. We don't know if the same models that we use in Barrow would be appropriate in the Lena, for instance, and vice versa, right? The European community has sort of seen similar things. In terms of things that a National Academies workshop could further, I think sort of the synthesis of observations, but also the synthesis of modeling efforts in a suite of areas would be very, very welcome.
Thank you, Charlie.
Yeah, and then just following up on Ethan's point, I guess I want to make a very similar one, which is that, I think those of us in the US working on ESM development sort of talk to each other a bunch. And, I think that the different Earth system modeling centers around the world are all, they're all thinking about these things and coming up with different solutions. And I think getting that kind of dialogue across the international Earth system modeling centers would be very valuable.
Bill and then Eugene.
I was just going to say, following on those comments, you can imagine a data synthesis being a framework in which a model and a comparison could occur. So I don't know if we could do this all in one meeting, but you synthesize the data, come up with metrics, bring the models together maybe beforehand, have them run, and then get together and see why they all failed. And which, whether serendipity was the reason one of them succeeded, or if there was a real process reason they succeeded. But you could really link those together in that way.
Thanks, Bill. Eugene.
Hey, sorry, I joined late, so I missed most of the talks, but I just want to kind of mention that, definitely the main framework here, like the integrated kind of Earth system modeling, bridging different skills, is something very kind of much along while with the DOE's energy SQ Earth system model development kind of idea. So so I think the ESRSM team will be interested in kind of this kind of discussion. I think probably the DOE means there's something here and the renewable power mentioned it already, but just in case. Thanks.
Dave?
I think one thing that Charlie said, talking to the other modeling groups, I think there's also this different scales of modeling discussion like Bill showed. I mean, obviously the work that we're doing is very parallel, really, just emphasized for different scales. And I think that the likelihood that we're going to get to a stage where Earth system models are simulating thermokarst is probably fairly low, but we might be able to simulate thermokarst vulnerability, potential thermokarst, and then to feed into another model somehow to get the impact. So I think it's probably going to be too complicated on any near-term timescale to have an Earth system model, really modeling thermokarst. So we need to think of ways to take the best of what the Earth system models can provide to feed into some separate assessment. Unfortunately, it'd be nice to have it embedded, but I think it's going to be tough.
Anna, do you want to quickly mention your comments to the group? And then Renu.
Yeah, along the lines, I mean, a lot of people are discussing, talking about not just observation to observation comparison or model to model comparison, but doing similar things all together, like observation comparison, model comparison, observation and model comparison. So Eleanor Burke, leading one of the Jules model researcher, she's one of the those who are leading Permafrost MIP under the EASY MIP, intersectoral model intercomparison. And she has been discussing conducting or coming up with protocols where we can compare model to observations or model to model, but also conducting simulations with various models where, for instance, 8 Mile Lake has done a lot of different experiments, and whether we could simulate these things with different models. So we have been discussing these things, and Eleanor is working on coming up with a protocol and then putting together data from different sites. For instance, I'm working on a Pulsar-Meyer environment where there's quite rapid thawing and subsidence occurring in these areas with a lot of changes in CO2 and methane emissions. And I can see that there's many different groups working on this kind of pulsar degradation environment with permafrost. So it would be interesting to compare these things, but also we have been using CLM and Jules to model the site. And I think it would be quite interesting to put these efforts together to make comparison to understand what are observations actually capturing, and then what are the models capturing, and what are we missing, and what processes are really important, and some of them are not incorporated that are important. For instance, recently we're finding out that nitrous oxide emissions is quite variable, and it has some effect because it has quite high global warming potential. And we have been only talking about CO2 and methane, but we could potentially also consider nitrous oxide in different sites. But if those who are making observations have not measured nitrous oxide, then we don't know what is happening. But I think it would be interesting to combine efforts to make easy comparisons.
Great, thank you. Renu?
So I do have lots of questions, but I'm just prioritizing two. One is a follow on to what Dave Lawrence mentioned. It's maybe models are not at the stage where we can get all the processes in, right? So what are the immediate next steps? And is there a possibility in the next, how long would it take to get, may not be fine scale APS Amansi kind of code in, but something a little bit more realistic? How much time would it take in terms of that? Then the other thing is also, the permafrost carbon network activities are also there. So are some of this data synthesis kind of activities not being discussed there? Or, I just wanted to get a feel for that too. So data synthesis activities and, intercomparisons, I thought it was some of it was part of the permafrost carbon network. And so I'd like to know what isn't a little bit more clearly. Thanks.
Well, many of the activities in the permafrost carbon network have often relied on momentum within the community. So the meetings we had provided the logistical aspects of the meetings, and then modelers would come together with field people and then discuss what's next. And that's how some of the modeling work published by Dave McGuire happened. Currently, we do have a modeling component in the current permafrost carbon network activities. They are focusing a little more on CLM. So other models are still welcome to participate, but we are not currently working on a model intercomparison project. And we are still doing data synthesis. I can't say that right now we have one new project lined up yet. This is still work in progress under the new funding. Maybe Dave can speak to that too.
Well, I think what Hannah was saying is kind of interesting, that they're doing some experiments related to the 8 Mile Lake and maybe Escorus as well. And, you can envision we could develop some sort of a protocol to test these models on a more process level, some sort of MIP. And that was the idea with what the project that Christine just mentioned, is that we were trying to develop some sort of protocol within a CLM context that we could then apply to other models. But we didn't want to waste everyone's time, doing experiments that we didn't know were going to be meaningful or we could even learn anything from. So that's a potential thing that we could get to. To answer Rena's question, I don't know the time frame of when we could model. Modeling thermokarst within an Earth system model is just going to be really challenging. So I personally don't have a vision for how to get to that right now. Maybe that's what a workshop could help us get to. Or maybe it's going to be, like I said, more like a crosswalk where the Earth system model provides a vulnerability map, and then you use that vulnerability map to make a further assessment.
Our time is kind of up, so I don't know if we have an opportunity to continue the conversation, or April and Laura, maybe you have one comment.
I would just say thanks again for this. I've been frantically taking notes, as I expect Lori has been too. And I think you've given us a lot of food for thought for this. And I think we will definitely be circling back with some of you about this as we continue to try to develop something.
Are there final comments by any of the participants? Well, then otherwise, I would also say thank you very much that you all participated. And this was really interesting. And I do hope that we will continue the collaborative approach of including scientists from different disciplines and countries and models. I do think that's important and has been a goal of the Permafrost Carbon Network for sure over the last years. Thank you.
Thank you.
Bye-bye.
Thank you very much.
Thanks, everybody.
Thank you, everyone.